We'll do some announcements about all the social activities later. I want to make a summary of where we're standing, and if you missed the poster session because everyone was having breakfast, but you're still interested in some of the posters, you can just write to this person on Discord to arrange another view. Okay, so today is a bit of a change of topic, so I thought I'd just recap the. So on Monday, we talk about resource versus quantum thermodynamics, right? So we start with the introduction, and then we saw some applications for processing, we saw some applications for networks. I saw how to perform this very idealized things, idealized resource theories. Great ones, for example, what Rob said, where we only allow for autonomous engines, not very fine control over militaries. So we did all this, but this was all possible, right? So today, if you remember in the beginning of this lecture, at the very beginning, we said resource theories, you just need a set of all the operations and everything. It's not necessarily a quantum thing. So today we're going to go to even more abstract systems. So what Renato and Ladina will talk about is not necessarily quantum. So in fact, it is a revamping of some of the systems at the very beginning. So thinking of classical large correlation systems. So it will be a very abstract thing. And then the nice thing about this is that you can apply very different and sometimes surprising systems. So in particular, what Ladina will do is to take what Renato's framework, and then she will apply it to black holes. So today is like the more theory day of the summer school, and for all the experimentalists in the room, I have good news, which is that quantum systems. So we'll talk about some phenomena and then apply them to each system. So there will be thermalization, like how do we reach this given state, this thermal state? Thermal engines, model thermal engines, and also how to measure temperature of systems. And we'll look at both superconducting circuits systems. So Patrick will talk about this, and many-body systems. Alvar will talk about this. Okay, so this is just where we stand. And now here's Renato Renner, who's the expert, and he will tell us about semantic approaches in thermodynamics.
Okay, thanks, Lydia. So before I start with the talk, I was asked to make a bit of, or give an announcement or advertisement. So maybe you know we are here in this so-called Swiss Map Research Station. This is actually it's a new thing. It will be officially opened only in 2 or 3 weeks from now. There will be a small ceremony. This room is completely new. And those who had some winter schools or summer schools here may know that we had a very small room and it wasn't part of this Swiss Map thing. So Swiss Map is a Swiss network of mathematical physicists. And as part of their activity, they want to have regular programs here. And this is in a way, or should be in the future, a conference resort for events of this type. There could also be smaller workshops that you could have here or larger events, which the center of Diablerets. The reason I'm telling you that is that if you are yourself interested in organizing an event of this type, or a smaller or larger one, then you may actually apply. There's also funding you can get from Swiss Map, from this network, and you will find on the webpage the relevant deadline. I think one of them is pretty soon, and I think we will every year again have an opening for calls for proposals for workshops and conferences. And I hope you saw that it's a very nice place and enjoying it. And I think it's really an optimal place to also have different events, workshops where you of a retreat type, because no one can escape here. So, I'll talk about axiomatic thermodynamics, and I would start telling you why I'm doing that. Lydia already said that it will be a preparation for what comes later today, and the application will be a kind of far-fetched application. You will see how this whole thing is applied to understand black holes. Now, my personal experience from learning thermodynamics when I was a student was that it was a rather frustrating thing to do, because there were different concepts introduced in a way where I was never sure whether these are now basic concepts or certain things that are derived, or what's the status of these things. For example, at some point I started to talk about temperature or about heat. I would ask, is heat now something that was already defined or not? How should I understand it? And in a way, this, let's say, next 2 hours are an approach to make this whole thing more, I shouldn't say rigorous, because that sounds a bit formal, but let's say to give the whole thing a more well-defined logical structure, and to see what is actually derived from what are the postulates and what are the derived notions. So, for example, we'll see how the notion of temperature is something we can derive from much more basic concepts that you can understand without already knowing thermodynamics. I mean, it's kind of strange if I would tell you, look, we have here two bodies and they have temperatures, and let's define the temperature in such a way that it corresponds to what we experience as temperature. That's not very satisfactory, in particular not if you go to applications such as the one we will see later today, black holes. When we talk about black holes, it's obvious that these are objects we cannot actually make experiments about. There's no experimental evidence at all that black holes radiate, that they have a temperature. Of course, we have now seen them. You've probably all seen the photograph. But just to be clear, this statement that black holes radiate, which is a well-known statement, Hawking radiation, is something we cannot experimentally verify, probably also not in the midterm future. Nonetheless, physicists are very convinced that they actually do radiate. And the reason why they are so convinced is that there are many different, I would say logically rather independent arguments that all lead to this conclusion. And if you have several arguments based on different assumptions that lead to the same conclusion, you can somehow be confident that there is some truth to this. Now, the thermodynamic arguments that you will hear about today are, of course, based on thermodynamics. And then to make these arguments more consistent and also grounded, you need a framework where you understand what are these notions. You cannot just introduce temperature on the intuition, because this intuition may not apply to black holes. So that's basically all that we want to come back to very basic notions like temperature. And at the end of my lecture, we will just be at the point where you see entropy, and we will prove, for example, that the entropy can only increase in a system that is not in contact with anything else. So that will be basically the culmination. So we will not get that far, but the point will be that you will see how these notions are based on more basic concepts and this whole logical structure. So in a way, it should be a review of things that you have already learned as a student, and maybe putting things into the frame, which allows you to understand much better why things were introduced in a particular way, or maybe they were not. Okay. Now, so what is an axiomatic approach? An axiomatic approach is something which you could compare, for example, to group theory. So maybe in the old times, people didn't have the theory of groups, but they were already multiplying numbers. Maybe they were even multiplying matrices. But then at some point, one realized that all these different things, I mean, multiplication occurs in many different contexts, have always the same kind of basic properties. And these are the properties we now call the defining properties of a group. And nowadays, we just introduce groups as abstract objects, and then we can already prove lots of things just based on these very abstract notions without knowing that the group elements will later, for example, be matrices or so. So you can, I mean, there are many extremely far-reaching results in group theory. And the way I will introduce thermodynamics is a bit similar. We will just start from a very general structure where we will not need to know what the underlying systems really are. And this is a big advantage. That's even something we need to do, because we know very little about black holes, for example. So it's very good if you have a theory that allows us to know only minimal things and already be able to work and prove theorems about these objects. And actually, this is just a historic remark before I start with the actual and more technical content. The situation was very much the same 200 years ago with gas. I mean, today, what is today a black hole was at that time a gas, if you want. It was a kind of black box. People didn't know that gas consists of molecules, or fluid consists of molecules. It was basically something that had some behavior. They knew some things about them. For example, you can compress the gas and you can see what happens, that it heats up a bit and so on. But basically, that was all you could do. You could describe a gas with some macroscopic variables, volume, pressure, and temperature. And these are exactly the things that appear then in the frameworks that we are in thermodynamics. And we are exactly at the same place with black holes. We can characterize them with some macroscopic variables. They have a mass. We also know they can have a charge and they have an angular momentum. But according to the classical theory of relativity, that's all. They don't have any additional properties whatsoever. And of course, that's just what the theory says. This doesn't mean they don't actually have other properties. That would be a wrong conclusion. But the theories we have only describe these properties. So all we can say, which is well grounded, namely on established theories like classical general relativity, are things which have to be reduced to these very few variables. And so the whole theory, the idea is based on the approach of describing systems about which we know very little. Okay, now, the last thing I want to say is that what I'm going to present is to a large extent taken from a PhD thesis from Philipp Kammerlander. We worked this out together. Of course, the whole thing is based on many previous works and discussions, also with people who were in my group, like Lydia, Philipp Feist, who is here as well. And if you are interested in more details, then I would recommend that you just have a look at the PhD thesis of Philipp Kammerlander, which is available online. And for those who speak German, I also gave a course in thermodynamics this last semester, a bachelor course. It was in German, which is recorded, but you can also download the lecture notes, or okay, I'm not sure it's actually available, but then write me an email if you're interested and I can give you access to that. But the videos are certainly available. Okay, let's now start. So the way you should write the title first. For axiomatic, I hope I now motivate well. So axioms means we are really trying to make explicit all the assumptions that enter the theory. And things like the first, I should say that already now, things like the first law of thermodynamics or the second law of thermodynamics will in a way be axioms. So that is already a statement. We will not be able to prove them. They are basic axioms of the theory, like the force law in Newtonian mechanics. Now, I would like to start with a picture. And by the way, I will not be able to make everything rigorous. So there's a distinction between making things rigorous and pointing out the logical structure. So you have to somehow believe me that things I'm not going to prove are true, and you can look them up in the thesis of Philipp Kammerlander. And I will put the focus in this lecture, just for reasons of time, on the overall logical structure and what the things are. But please don't hesitate to interrupt me at any point. It's important that you interrupt me, because otherwise it will be a lost day. Because I think most of what you're going to see today will be based also on parts of this framework, also in the talk later by Ladina Hausmann. Okay, so the picture one should have in mind is that we are in a world which has objects, and these objects are typically now objects that are relevant in thermodynamics, like a little piston that we can press. Maybe there is a kind of a reservoir. Think of a reservoir maybe as a little lake, and maybe there is somewhere else another piston that a cylinder with a piston, with a gas in it, and there's some fluid in it, in this one. And maybe there is also other things like a black hole. I don't draw it now. But you could think, maybe I should actually draw it, because there are also processes. I mean, in the same way as I can, for example, compress a gas and see what happens, I can do stuff with a black hole, in principle at least. So one typical experiment that you can do, or process, is that you take a little mass or a box with something inside, could also be radiation inside, and you put it on a little generator or something. So there's a little wheel that when as you lower the weight towards the black hole will of course attract this weight, you generate energy that you can put into a battery. So battery, and you charge this battery via the process of lowering a mass towards the black hole. I mean, the same I could do just with Earth, but interesting things will happen when this is not the Earth, but the black hole. So just to give you one little, let's say, idea of what amazing things can happen here. You don't need to now think too hard about this. Maybe I hope it's not confusing. Is, for example, if you put here a mass and you lower it until the so-called event horizon of the black hole. This is the point of no return. If you would lower it further, you can never draw it back again, because everything will then hit the singularity. But if you do that in an optimal way, so you do it adiabatically, very slowly, and you really get all the energy out, then the energy you will have at the end in this battery will be exactly equal to the mass that you lowered. I mean, there's of course this energy mass equivalent, so the energy will be n times c squared. So you basically get all the mass that you have here back as energy. And this is something very remarkable that leads to potential contradictions, and we will hear more about this later. There will also be a very nice exercise that, by the way, Julia designed. I should give some credit to her. This is a kind of maybe more an explanation than an exercise of this process and the thermodynamic implications it has, and how we can already use this process to understand black hole radiation. So these will all be things you will hopefully be able to understand. So at the moment, I just drew these things to make the point that we have a world, and we think of in this framework of the world consisting of thermodynamic systems, and we have kind of a limited access to them. So for example, here we can determine what's the volume of this cylinder. Maybe we call this V2 and this is V1. This is another cylinder. Maybe we can also measure something like pressure. Pressure could be measured here when we push the piston in. Now I will not at this point talk about temperature because we haven't defined it, but you could of course just still connect a little thing that we would call a thermometer, which would at this point just be defined by something which looks at the expansion of some fluid, as a conventional thermometer does, and say, okay, this is something we can measure. What's the expansion of the fluid when this is brought into contact with this reservoir? And of course, later one will see this corresponds to temperature. For a black hole, we could, as I said, put this or measure the mass m of the black hole via its potential that it creates. So we can assign quantities to this system and also execute processes. And this was one example of such a process. Now the idea will be that these quantities correspond to the states of the system. So when I will talk about states of a system, I don't mean the microscopic state. This will be the state will just mean what we know about the system, or even we could even say what we decide to know. I mean, today we of course know that gas consists of little molecules, but I could still decide to describe the gas only by the volume and the pressure and maybe the energy that is in it. If I like, so I could just ignore certain information. And the thermodynamic framework, this axiomatic framework, is exactly a framework that allows us to talk about such limited information. So this is important. So whenever I talk about state, don't think of this as a quantum state, which is kind of the opposite. The quantum state really this tells you, if it's at least if it's a pure state, about every single microscopic degree of freedom of a system. Whereas here we know that if I tell you the volume, there is a huge equivalence class of systems that have the same behavior, so to speak. Okay, so that was more the pictorial part. Let's now make this whole thing a bit yeah, maybe just to save a bit of space, I will here make a two-column thing, and you see here, this is now just part of our thermodynamic world. I start with some definitions or postulates. So I will basically now go through a list of postulates, and each postulate introduces or states something, which hopefully should be rather intuitive. You should ideally say, oh, this is just trivial that this is true, or it's clear that this should be true. Maybe except for the first and second law of thermodynamics, which is, of course, kind of in some way highly non-trivial postulate. Okay, so postulate one, I will number them, but this is not kind of an official numbering. I think Ladina in her talk may use the same one if she uses numbers, but otherwise the numbers have no significance. So I think of this thermodynamic world, first of all, just as a set. So like in group theory, there's first of a set, and then we equip this set with a composition operation. So we have like the thermodynamic world. So this is just to refer to this picture. That will not be a technical term. Is a set which I call omega, and this is just in a way you could think of this set as this whole domain here. And now if I want to talk about a particular system, I will kind of cut, for example, I want to talk about this this little cylinder and piston. I can cut out the part of this world and call this system this, for example. So you have this set I will call omega, and then a thermodynamic system. That's now the first term. That's kind of what the postulate says. It's just a subset of omega. So if you call it subset S of omega. So whenever I talk about as a thermodynamic system, I just mean a subset. So this could be just one thing, but a thermodynamic system could also be a combination of, so this would also be a thermodynamic system. Let's call it S prime. And of course, I can now combine thermodynamic systems. I could say this is a thermodynamic system. It's in here. That's another thermodynamic system. Now I run out of, okay, I don't want to have primes all the time. Let's call it S1. And then there's another one here. S2. And then an S prime would in this case be equal to S1 combined with S2. And we can use basically the notion of combining sets, but instead of combining set, I mean, of the union, I will write this little symbol here because, okay, I mean, maybe the reason will become clear later, but just understand it at the moment as a set combination. So this is just now a language to talk about this as a joint system. So far I've done almost nothing. I've just introduced, I mean, when I talk about the system, you could ask, what is it? And now the answer, it's just a subset of the thermodynamic world. This is true independently of thermodynamics, of course.
Just a little bit confused. So you define something like the thermodynamic as a subset. Mm-hmm. So does it mean that it's a set including some physical properties that you haven't defined yet, like the temperature, or You just
Yes, okay. This is good that you asked. So this set omega, this is not about properties. You could think of, okay, we will never say something more about omegas. You could say, but if you want, you could say omega is just the collection of all, let's say, atoms, for example. Then you could say the system S is defined as the subset of all atoms of the world that consists this particular system I'm interested in.
okay.
But I will never then go into this fine-grained thing and describe the individual elements of omega. So the only thing we will do, and this is a very good question, we will only talk about these subsets. We will never go down and say, okay, now we look at individual elements. So basically I could say, for example, this room is this set omega, and one table is like a subset of the room. And now I haven't said whether, when I consider the room as a big set, whether this now means the abstract points like the coordinates or the atoms in the room. This is irrelevant. The relevant thing, and that's actually one reason why we use this operation on, in the actual framework, we don't even say they have to be subsets. We immediately start and say we just have such a combination operation. But this combination operation satisfies all the axioms of set union. That's why it's easier for the efficient to say, let's start with this set and then have this system that we can combine. So basically, the only thing I said so far is we can cut out the part of the world, and this is a system. And now we can, of course, combine systems. But the important thing is that if you combine systems, so if I, for example, combine S prime with S1, so I could write such a thing like S prime combined S1, then this is, of course, again, S prime, because S1 was already part of that system. So, and this is important to notice, because if I take twice a system, let's say I could even write something like S1 and S1. This is not twice the system S1. It's again S1, because I just took twice the same part of the world. And this, so you shouldn't think of a system as a copy of something that does the same. So, for example, if I think, maybe that's something I should also mention. If I think of a cylinder, I could say this just means now 2 cylinders. But the system S doesn't mean a cylinder. It means this particular cylinder that is here. And now, of course, if I take this twice, this doesn't make sense. I cannot take twice U, for example. So it's really a personalized thing. A system is a system somewhere, not a system of a certain type, so to speak. Are there other questions about? Okay, so actually the first 2 axioms will have very little to do with thermodynamics. They're just, I need them to even talk about, to sensibly talk about things like systems. I hope it's okay if I erase this.
Yes, you can erase it.
Now will be another kind of boring axiom. We will now have to talk about the states of the system. So far systems don't have even properties, they're just labels. So now a way to label the world. Same axioms would apply if I just, for example, take this to describe groups of people. Like omega would be the whole population of the world, and this is just a group of people or an individual also. Okay, now there's a postulate 2. Lydia, for the camera, is it better if I put this down and or
it's the same.
Is this too low?
No, that's okay. But for the people on the back,
oh, yes.
it's better.
Yes, okay. Well. I will have a postulate 2. So you see the numbers increase fast without much happening so far. And postulate 2 is about states of these systems. So we could say, and I will actually distinguish it into 2A and B. And the reason I put it A, B, not 2 and 3, is that I want to be compatible with the numbering in Philip Kammerlander's thesis, in case you want to look up the formal version of these postulates. So everything I say can be stated very formally, and you see all these formal forms. You can read up on them in this thesis. So the next postulate is basically each system has a set sigma S of states. That's also kind of clear in most physical theories. We have that, that the system has a set of states. Now, for S is itself consisting of two subsystems which are disjoint. S1 disjoint. So that's the usual thing, like we had it in this drawing here, that we have different systems which don't overlap. Then the state should be, I mean, there's an additional requirement. Then this set should itself be a product set. So this is actually an important assumption, which is a bit in contradiction to, if you see this the first time, you would say, oh, this excludes quantum systems. Because what we are saying is basically, if I describe here this, now I assign to every system a state set. So this cylinder here has a state set, this little reservoir has a state set. And now you could ask, what's the state set of the joint thing, of the orange thing? And now everyone who has heard quantum mechanics would say, of course, the state set of the orange thing shouldn't be just the product of the state set of this and the state set of this one. And that's true. But remember that we are here just talking about macroscopic observables. We are not talking about the microscopic state. So even though the microscopic state of these systems may be entangled, we can still, and that's kind of what the postulate requires, talk about, for example, the volume of this and the volume of this separately. But what this postulate implies is that these macroscopic quantities that enter thermodynamics have to be somehow classical quantities. So we cannot, within that framework, now talk about a system which is where the volumes themselves are entangled, for example. And I mean, this is just, you could say this is a limitation. And I think it would be kind of an open problem to generalize the framework to the case where even the macroscopic variables will be quantum variables. But this hasn't been achieved. It leads to rather fundamental problems. People don't know how to define the latent temperature and work of such systems, or at least there's no agreement how to do that. You can't do it. So the framework stays here in a kind of safe domain where we say whatever we can say about the system on a macroscopic level has this structure that we can really assign a clear meaning to each of the subsystems. Okay, so in other words, to summarize, this postulate says that if I have a system which consists of subsystems, I can decompose the state into the subsystem states and say, okay, this subsystem is in a particular state and this one. So just to give you now an example, like for example, the sigma S, I think S1 here was a cylinder, could just be a set of the form like the usual thing you have in thermodynamics, that you would, for example, say you specify the volume and, for example, the or let's say the particle number n, the volume, and let's say the energy, total energy of the system. And of course, these are all in certain ranges. For example, this is something larger than 0, and B is larger, strictly larger than 0, and E is some, let's say, real number. So this would be a state set of a system. So that's what you're used to. That's in thermodynamics, we assign certain numbers to a system. And of course, the framework doesn't constrain you what they are, just says it has to be some set. And the set has to be kind of well defined for each subsystem. Okay. Now there is obviously a postulate 2b, and this is maybe we are still in the part where I introduce very basic notions. Yes.
Does this formalism allow for fluctuations?
Oh, that's a very good question. Thanks for asking. I should have mentioned it. Yes, this is an extremely good question because in thermodynamics we usually say, when you learn thermodynamics, people say very early, we look at equilibrium states. Now, I cannot do that because we haven't defined what an equilibrium should be. So actually, you will see what we require will not force you to restrict to equilibrium states. The only thing you're requiring is that if you have really a real physical system, you can extract this number and say what it is. So of course you can do it for volume and pressure, but let's suppose you have a system which is actually oscillating. Then you could say, oh, this still has a well-defined number. For example, you can extract the oscillation frequency, or you can extract the average of the volume when the volume oscillating and then say this is now the quantity I consider. So if the system is in an oscillating state, I take this. So the only requirement is you have to have some means to assign a definitive number. Of course, if the system is kind of completely chaotic or something, then you cannot do that, or you probably don't find such a number. But as soon as you can somehow extract the number from the system, that's allowed. You don't need to worry whether the system is now in an equilibrium state. And that's really an important part, because that's exactly one of these things that makes thermodynamics a bit strange, that we say, oh, we only look at thermodynamic equilibrium states, and then people ask, what is that? And then you have to somehow wave your hands and say, oh, this is somehow a new weight law and so on. But yeah. Okay, thanks for this question. So the next thing is about processes. And here I draw now a different picture. It's also a box that I draw, but you should now think of this box as the state space of a system S. So I take a system and its state space, and this state space is typically maybe continuous. It doesn't have to be, but it's typically the case. And now one point in this state is just one state. So that would, for example, for a gas be a particular number in one of gas particles, a particular volume and a particular energy. And then I have another state here, maybe some other, or maybe it's in the same number of particles still, it could also be. And now I could ask myself, is there a way to turn a system that is in this state into that state? And if that exists, then I could draw here a line somehow and say, there is a way to turn, for example, to compress a gas. I mean, this could be a system which is an expanded piston, and this could be a compressed one. And then if I draw this arrow, this means there is a process to compress it. Now, how do I capture this formally? I just say there exists a set which I call calligraphic P of, which I call the set of all processes. What are these elements? So a priori it's just a set. And now each process in this set, so I call the individual processes little p, that's one of them, defines a system S. It involves or acts on, I think the usual terminology is that it involves system S. So, I mean, for example, if I say I compress now this cylinder, then this process involves exactly that system S and not that part. But if I, for example, say I bring this system into contact with this thermal reservoir, that's also a process. That's something I can do. And that's a process that acts on the joint system S1, S2. And, okay, so first of all, for each process, I can determine what is the system it acts on and an initial state. So this is this is the notation used for the initial state of the process on the system S and a final state. That's kind of also very basic. You would say, okay, a process is something that has an initial state and it has a final state. So importantly, a process is not a function. It's not that P tells me for each initial state what is the final state. One given process is really, I take the gas at this particular volume with this particular pressure and compress it to that. And if I start with a different volume, it's a different process. But that's just a kind of terminology. So a process defines uniquely the initial and final state. That's what you should remember from this.
Renato, just to clarify, if you have two different ways of compressing a gas with the same initial and final state, is it the same process or different processes?
Yeah, that's good. Thanks for my. No, it's not. So a process defines the initial and final state, but it's not necessarily true that if two processes have the same initial and final state, they are the same processes. And this just captures the fact that, as Lydia indicated, that there could be very different ways of achieving the same transformation from an initial state to a final state. There would be different elements of this set, but they would have the same initial and final states.
And you could only differentiate them once you describe how the system is, or at this abstract level you can already differentiate them somehow.
Yeah, we will later see. We will add additional. So, for example, processes will also have a work cost. So they will have additional properties, and so these could be reasons to differentiate.
It contains also information about the trajectory in device.
No, okay, that's also a very good question. So at this point, you only need to know the initial and final state. So it could be, and that actually relates to the question about equilibria or thermal equilibrium. Let's suppose, one possible process that is often considered is the following. You take a gas cylinder, whether there is a wall in it and the gas is on the left-hand side, and now you remove the wall, and then the gas is somehow distributed over the whole cylinder. So that's a typical process. Now, in this process, maybe, when you remove the wall, obviously the gas will not immediately be here and so on. So you could say, in principle, it goes through a trajectory, but it would be very hard to define what are the states in between, because this would now be some microscopic things. So to require that a process has a continuous trajectory would be very restrictive. It would potentially exclude such processes. And so, remember, in an axiomatic framework, we only want to require the minimal things that allow us to define everything we want, like temperature and entropy. It turns out we only need the initial and final state. There are, of course, special cases of processes that you can see as an infinite concatenation of very small processes that you can do. So this doesn't exclude you or prevent you from describing it continuously, and that's, of course, what we often do, but it doesn't force you to describe it continuously. So maybe I shouldn't have drawn, this arrow is really something that starts here and ends here, and there's nothing in between, so to speak. So the pictures in that sense maybe not optimal. So the arrow is in a way no part of it. It's not a path.
But they are not the ordered couples, because several processes may have different processes may have the same.
Yes, right. Yes, exactly. Yes, that's also what Lydia said. So if you only know the ordered couple of initial and final state, that's not defining the process. The process has this property, but two different processes could have the same ordered pair of initial and final state. And also, by the way, that's obvious. Processes are obviously directed. That's the other thing which is. Yes.
Yeah, excuse me. When you were introducing P calligraphic at the beginning, I understood that it was all the set of all processes that go from point A to point B. But now I'm understanding that it can be like from any point of S to any point of S.
So the set calligraphic P is all possible processes from any initial.
Inside of S.
Okay. Actually, the next thing, so P, the processes always tell us. So it is a property of the process on which system it acts, so to speak. So I could have a process acting on one cylinder and one on the other, and then the one acting on S only describes an initial state. So this is a state of sigma S, and this is also of sigma S. And then I could have another process which acts on S prime, and it would define an initial state. And
so we would first set a process P, and then that would give us the system that we're working on.
Yes, exactly. Yes, right. So the process defines which system it acts on. And actually a useful notation here is to say we restrict, or we can look at the set of all processes that act on a particular system. So P without a subscript, P without a subscript is just all possible processes of any possible system. Now it will be very useful to actually restrict sometimes to all processes on a particular system. And this is just a notation that I can now use. That's not a new postulate. I denote also calligraphic P, but with a little s, the subset of P consisting of all processes P that act on S. So that would be then, if I take something from that set, I know it's exactly, it acts only on S. And for those who may have, I mean, there could be some students here who took my lecture in thermodynamics, these would have been called working processes on S, but I will not use this terminology here. I will just say, use this set and say if a process is in this set, we know it acts only on the system S. So if it's on S, it's not allowed. So for example, a process where I take this cylinder and put it in contact with this reservoir is not part of PS1 because it also involves the reservoir. It's part of PS1 together with S2. So.
Sorry, some people cannot read your handwriting, so can you just read out loud everything that's written there and stand there while you say this to the camera? Yes.
Yes. Okay. Here, what I wrote is that we denote by P subscript S the subset of P, of calligraphic P, which is the set of all processes, consisting of all processes P that act on the system S. Should I write larger or just nicer? Or
Nicer would be good, but it's okay.
Okay.
Can I
Yes.
question?
Sure, yes.
So can you say that like this calligraphic P, the set of processes without a subscript, be akin to the set omega in a sense? Because like that's before you make a choice, a specific of system.
Oh, no. Okay. No, I think what I could say is P is the union of all PS, where a union is taken over all systems of omega. So you see, omega is kind of the world, the thermodynamic world, and all subsystems I have are, any subsystem or any system I have is a subset of this thing. So if I take now the processes acting on any possible subsystem and take them all together, I get back P. I hope that answers your.
Yeah. I'm just thinking like, because I took the postulate one as kind of you would like give a choice of S in principle. But then you go to the set of all processes, and then you also consider processes that do not involve S. Like, what's the use of that in a sense? Like considering
any
things at the same time, like processes that do not belong to S after you made a choice of S.
Sorry. Okay, maybe I was. So any process from P defines the system S on which it acts. So for any process there is an S. So that's now also contained in that statement that I wrote down. And so this first postulate just says what are yes. So this doesn't talk about processes. And then, first say what are the subsystems? They are subsets. Say processes act on a certain subsystem of the world. That's all we say. So far we said actually very little, which is in a way good because we say it and it still allows us to derive the things we want to derive, the better, because then the more flexible is the framework. So remember, at the end we want to ask, for example, is this framework applicable to black holes? So we really want to require very little.
So are these processes of a closed system? Are these processes all the processes that belong to the closed system, or do they include like processes of an external agent as well?
Oh, okay. So yeah, that's also an excellent question. So I assume that everything I mean, I have to include in my thermodynamic world all systems I ever want to assign properties to. Now, if I, for example, have externally some engine that is used to work on these systems, and I'm not interested in the properties of that engine, then I don't need to include it here. So in principle, a process could use some external system in a certain way, like an engine or a generator. For example, this generator in the black, I had this black hole picture of a generator. So maybe I would not describe the generator. I would just say there exists a process which lowers the weight and fills the battery. So I'm not forced to include everything, but some of the postulates will at least force me later. So for example, the first law will only be true if I include all systems that somehow contain energy in form of heat. So I cannot leave out too much, but at this point I haven't asked to include, let's say, everything that is around. Okay, thanks a lot for all these excellent questions. I think they're very useful. The important statements. The next one is just, now it becomes actually easier in a way, because it's usually hard to get the right way of thinking. I mean, these are kind of trivial statements, but you need to adapt your thinking to what are now processes. And now the next thing is just processes can be concatenated. And this is now, so for example, and I write for the concatenated process. So if I have a process P and a process P prime, I write P prime. Now this is a part where I'm not going into the details because it's probably intuitively extremely clear what I mean. I just do it graphically. So we said before that a process is defines an initial and a final state on a system S. And now I could, of course, have another process, like one that goes, for example, from this state to a state here. This could be another state. We call this P prime. And then, of course, the concatenation of this process and that would be the process that goes from here to here. And the axiom or the postulate basically tells me this is also an allowed process. I mean, it's obvious that we want that because, of course, we can of course, execute processes in a row. That's all what it says. So the framework has to reflect the fact that they can execute the process and then another process. Now, how this symbol is precisely defined is, as I said, I will not write down, but there are some obvious requirements. I mean, the obvious requirement is that the final state of P has to match the initial state of P prime. Otherwise, I cannot put them together. So this is a partially defined operation. And it's clear that the new process has the same initial, so the initial state of this joint process is, of course, the same as the initial state of P, and the final state of the whole thing is the same as the final state of P prime.
So you are requiring that the systems involved in the
Yeah, this is exactly one thing I wanted to mention now. That's also a very good point. So P and P prime don't necessarily need to be the same systems. I can still define a concatenation, which would just mean the following. So let's suppose I have one process acting on S and another process acting on S prime. And then the concatenation is just the process that does both. So this is just defined like that. But as I said, I will now not go into the details of that. It's just the obvious thing you would do when you concatenate processes. Just think of it, just you do both in a row. And if I would write down what this means for me, it would just take time, and I don't think give you much intuition. But as I said before, you can read up all these things in Philip's thesis, but this is certainly something that will not now hinder your understanding. Okay. Now comes, so far I could use this framework to do anything, to whatever. I mean, I haven't used anything that relates to thermodynamics. It's just about manipulating systems.
So, Renato, what you have used is all your time and a few I think so. Maybe we take
Break,
we
okay.
take a 5-minute break, and we try to restart at 10. Okay, so for people at home, it might be a bit later, but let's try. Okay.
So in 5 minutes we are starting. Oh, okay. Okay.
Okay, we are ready to restart. Noise.
Okay, so there's a question about
I have a bit of to that, like S1 and S2 are the systems, but not all the states can be disjointed, right? S1 and S2 are disjoint systems, but all the states on it need not be.
Oh, yeah, but this is now an assumption. So an assumption of the framework is that if we have a joint system, we can only talk about those aspects of the state that we can assign to the individual subsystems. Of course, as I said, we know from quantum mechanics that this is not true for everything, but because this framework is supposed to reproduce phenomenological thermodynamics, we only want to talk about the macroscopic things, and these are usually well separate.
Okay.
But as I said, to generalize the framework is kind of an open question, but we don't need that for all the applications. Okay, now I think you have seen the basic things, how these postulates are introduced. Now I have to go through a few more, and I will have to do them. I think it was important to see some in details, but I will not discuss all of them in that detail. But the next one is kind of the first one that introduces, as I already announced, actual thermodynamics. And it's the postulate, which I call here 4, which says the following. It says that for any system has a work function, which is a function which I call WS for work. It takes a process and maps the process to a real number. So what does it do? If WS applied to a process is a real number, and this real number should be interpreted, that's our interpretation, that the work put into the system. So you see, now you could regard this as an additional property that processes have. For example, if I compress a cylinder, I have to invest some work. And this work function, WS, tells me how much work I invested into that particular system. That, of course, depends on the system. I could have a complicated process that involves several systems with several pistons. And then I have here different systems, and I can hear this function tells me in each system how much work did go into that system. And that's importantly something we can measure. That's not a thermodynamic quantity yet. We don't need to know anything about heat and so on. This is something you could just compute, for example, using classical mechanics. If you compress a cylinder, you know the pressure and distance, and I think every one of you can calculate that. It's a bit more tricky for these processes involving black holes, but there, for example, general relativity tells us how to calculate the energy. So this will be important that we can, when we apply this theory, we have to figure out from the known theory, like when we apply this framework to black holes, the point will be we can actually calculate this function using general relativity. So this is something we know, despite the fact we cannot do actual experiments. That's something that comes from outside of the thermodynamics. That's something we have we draw out of the basic theory, so to speak, that describes the object, like classical mechanics or electrodynamics, and so on. Okay, so that's just the existence of such a function. And this also tells you now once more that even if processes have the same initial and final state, they could be different because they could, for example, use different work. Yes?
What does this function mean if the process is not acting on S? Or is it
yeah. Okay, that's a good point. I didn't now. It's actually an additional requirement which I now just left out for time reason, is that if the process doesn't act on S, then it's by definition just zero, which is the intuitive thing you would expect. Like if I compress this cylinder, then how much work is required for something somewhere else? Known. Yes. Thanks for asking.
So if the trajectory is not part of the definition of the process, you can think of two processes which have like the piston, you push it very hard or very slowly.
Yes.
They can require.
They could have different. Yes, right. So you could have the same initial and final state where you compress a gas, and maybe it's in contact with some, even a thermal bath. And in one, you do it very fast, and in one slow. And this could require different work. So there would be different processes because they have different velocities. And the calculation within classical mechanics of how much work they need would give you a different result. So that's fine. So that's why it's really important that even processes with the same initial and final state are different processes and can have different work. Yes. Okay.
What would be the only thing that you would make to defer different processes, except potential?
At this point, yes. I mean, one could then go further with the framework, but we will not need anything else for us. Yes. I mean, if one goes further and introduces thermodynamic potentials, we also need to look at processes that can be made smooth in state space and so on. But yes, for us, this is all that distinguishes. Now the next postulate, and now it becomes really easier because it's just stuff I don't even need pictures, is the additivity of W. So this just requires basically if I compose two processes under the assumption they are composable. They are only composable if their final state of this matches the initial state here, or if they act on different systems. But if they do, they have to be, the work has to be additive. That's something that is just true, usually in all applications because of energy conservation. So this postulate is a rather unproblematic postulate that is satisfied almost always.
Is this work function going from P or from PS? This is the question. Does it go from all systems or from?
Yes.
From all processes or just a process?
Actually, it's going from all P in principle, but it assigns if the process doesn't act on S, it assigns the value 0 to it.
That's a small question. So why if the process acts on part of the S? Like you have S there.
Yes. Yeah. So we need, now I talk about when it acts on S and when it doesn't. If it acts on part on it, one let's say, okay, I think to actually write down what precisely happens, I would need more time, and I will not do that here. You should just believe it can be done in a way which is consistent with these special cases. But to go into that, if you're interested, this is also in the thesis. But let's say, if you would define it yourself, you would probably do it exactly in the, I mean, it's just what you intuitively expect. You just take that subsystem on which it acts, and then it has the corresponding properties there. So there's nothing surprising happening there. That's why I don't cover it. We will also not need it. And we will either, I have to generally here leave out a few details, but the details I leave out, I can assure you, are not fundamental things. They're just technicalities that pop up and can be resolved, let's say, in the obvious way how everyone would resolve if you see that. Okay, now there are a few definitions that I will actually not write down. I will just tell you the names of it. So if you now think of processes, we will often have something like we have a reservoir. I mean, I didn't tell you what the reservoir is. So far, a reservoir is just a system, a thermodynamic system, but I call it R. We may have another reservoir, and we have maybe some other system S acting on them. This is like what a thermodynamic machine does. Like I mean, you certainly have heard of the Carnot cycle. It's a machine that interacts with two reservoirs and extracts work from them, or a heat pump is also of that type. Now we could say that the process that is going on during the execution of this thermal machine, during the thermal machine running, is a process P. Let's say P describes one cycle of a Carnot cycle. Now, P can have several properties, and these are the properties you're probably familiar with. So, for example, we can say P is cyclic on S. What it means is simply, I mean, maybe that I write down. So, cyclic would mean that the initial state on S, which could be a subject, so the process could act on a larger system. So, the process acts is maybe a process. So, P could be a process here on S together with the reservoir 1 together with the reservoir 2. But I could now say it's cyclic on S if I just restrict what it does on S. So look, what's the initial state on S in the process and the final state on S in the process? They're the same. So that's obviously a sensible definition. One can also say that it's a process is reversible if there exists a process, another process which just does the opposite state transformation. That's also, I don't think I have to write this down. So reversibility just means I can do the opposite. And the important thing, if I do the opposite, it should just consume minus the amount of the work that I invested. So that's, when I, in the future, will talk about reversible processes, that's what I mean. Now, I'll leave out one postulate, which is not so important. So Ladina will drop the postulate 6, but I don't think this is crucial for you, what you're doing. And now comes the next postulate. And, okay. Use this blackboard. So now comes actually the first law. So we needed all this preparation to be able to state the first law of thermodynamics, which is just now in the same sense as all the other things, a postulate. And maybe it's a bit surprising if you see that for the first time, because usually in thermodynamics courses, you would just, the first law tells you the total energy change of a system is the sum of the heat flowing into the system and the work done on the system. Of course, the problem is we haven't yet defined heat. And we don't know what heat is. And so we cannot write it in that way in an axiomatic approach. But and so the first law has to talk about something very different. What does it talk about? The first law talks about processes, which is maybe not very surprising. It says the following. So think again about the state space, sigma S of a system. And now take two arbitrary states, sigma 1 and sigma 2. So sigma 1 and sigma 2 are just two elements of sigma S. I call them, I mean, for obvious reasons, also sigma, because they're elements of the set sigma S. And now the first law says, for any sigma 1 and sigma 2 element of sigma S, here, there exists a process which only acts on S. So PS is the set of processes that don't involve other systems. So I can do something only on the system S with the property that the initial state is just sigma 1 and the final state of the process is sigma 2. So that's one part. Or, and this is, there exists a process P prime. This is really or, such that the final state of P prime is sigma 1 and the initial state of sigma pi prime is sigma 2. So what does this tell us? That's, by the way, not yet the full postulate. That's the first part.
What's the notation there? The last P prime? With the brackets.
Yes.
Oh, yes, that's a strange bracket, yes. Okay. So that's basically telling you either there is a process, there's an arrow from left to right or one from right to left. That's what it tells you. So either there is this, that would be the process P, or there is that. So we can always, for example, when we have two states of a cylinder of a gas, and we can turn one into the other. For example, we can, if I have, let's say, one cylinder with a cold gas and one with a warm one, you can turn the cold one into a warm one by, and this is important, the process only acting on S, which means you cannot put it in contact with a reservoir. That's not allowed. That would not be the case. But you can still heat up the system, for example, just let's say compress it and do that many times, and then using friction, the system will normally acquire a larger energy. So there is a process to heat up a cylinder of gas but there is no process to cool it down without involving another system. And the first law, this part of the first law tells you just somehow the states are still connected. You can always go in one of the two directions. And now the important further part is, furthermore, the work of this process P is independent of or on, maybe I should write it like that, only depends on the initial and final state, and the same for P prime. And so basically it says that any process that only acts on the system, it doesn't involve reservoirs, will, if you turn one state into the other, will require the same amount of work. That's a postulate, but you can imagine that this, of course, reflects the true physical situation, energy conservation. If you only act on a system, then the system cannot, by definition, cannot exchange any form of energy with something else. And by the way, this relates to the question that was asked about what do we have to include. So this postulate forces us to include in the framework all systems that are relevant. And if I now say the process is in PS, it means the process only acts on the system S. And if I only act on the system S, energy can only come from the work I invest into it. And then however I do that, it will require the same amount of work. Okay, now, given this, we can do a definition. The definition, I will also just use the picture, is the definition of internal energy. So what's the internal energy of a system? We call it U. And U is depending on the state of the, so sigma is the state of the system. So sigma is just something in sigma S. And now U of sigma is defined as the work of a process P plus some reference energy. So internal energy is always defined up to an arbitrary reference with P is a process in PS such that the initial state of P is some reference state, sigma 0, and the final state of P is the desired state, sigma. So let me illustrate that in the picture I have above, then it's probably becoming clear. So in order to define internal energy, I just fix some state here, sigma 0. And I say by definition, U of sigma 0 is U0. So this is just some reference. Yes?
This P prime is just another process, or is the reverse process?
No, it's actually, yeah, this is a good point. I use this part because P may not have a reverse one. So in the example I gave where you have just a gas that you can heat up, there's no reverse. So if I heat it up by friction, there is no reverse thing. Okay. So now if, for example, sigma 2 was the cold gas and sigma 1 the warm one, then there would not be a process from sigma 1 to sigma 2. So P simply doesn't exist in this case. So there is no P here. And but however, there is a P prime. I could also here have called it P as well, because only one needs to. Yes?
You say only one needs to exist, but both may exist?
Yes, both may exist, yes. And actually, I didn't write it. If both exist, then this WP of the two have to be the same up to a sign. I didn't write this here, but this is somehow should be included in this informal thing, that it only depends on the initial and final state.
And for your definition of the internal energy, don't you need to be able to go to any state from sigma 0?
Yeah, okay, that's an important point. Now, indeed, this would not be sufficient because I cannot do it. So now the definition is like that if this exists, and now there comes again an or. So I have to make the same case distinction as before. So I'm actually not yet that or. And now you could say, well, that's a strange definition. It has an or in it. It's actually minus here plus u0 with, and here P prime is exactly the opposite process. It's one that starts with sigma and ends with sigma 0. So that's, you're almost faster than I am. That's part of the definition. Okay, so the definition basically says if I want to know the internal energy, take some reference and look at the process from the reference to the desired state and check how much work I need. Now the trouble, as you pointed out, is there may not be such a process from sigma 0 to sigma 1, but the first law guarantees that if there is none such process, there is certainly one from sigma 1 to sigma 0. So I just use the opposite one to define internal energy. And of course, that's also consistent. I can just ask if I go from that to that, how much energy does it consume? That's why I put here minus. Now there's a little thing one has to prove, because that definition may not be well defined. So first of all, it could not be well defined because I say in the definition it's defined like this or like that. So it looks like you have a choice. You have an even much larger choice, because here I'm just saying for some process P, but it could be that if I take different processes P, I get a different U. However, the first law exactly tells me that this WP only depends on the initial and final state. So using this first law, I can prove that this is actually a well-defined function. But this is a proof one has to carry out. Yes?
Just to be sure, the first law says that if your system is closed, then any process going to from A to B is equivalent.
Yes, any process that only, yes, the closed thing is important, that only acts on that system, yes. Yes, President.
So in the first formula, you mentioned WP. Since you have mentioned P, isn't it better to say U sigma 1 equals to WP plus U sigma 2 equals the WP plus U sigma 1? Because you have mentioned this W is for this process.
Sigma 1 and 2, or you're talking about this board?
No, the first.
This one?
Yes. This, when you say WP, it means that the work done in the process P, yes?
Yes, exactly.
So delta U should be for the initial and the finals.
Yes, so
state of the process. So
I should write here S, because it's on S. But yes, so here I say the initial state is sigma 0. So this P that occurs here in this line, you should really think, I mean, if this was sigma, this sigma 1 here, then the P would exactly be the thing from here to here.
So P is here.
Yeah, so the P would be that one here. Yes.
Yeah. So, but does U not correspond to the energy of sigma naught? Or
yes,
and then we have to establish some kind of reference.
That's yes. So this equality actually follows from the definition, because of course the process that brings sigma 0 to sigma 0 is a trivial process, and one can show from this additivity postulate that the trivial process has to have work 0, and so from this it follows that sigma 0 actually has U0. So that's a good question, because that's maybe not obvious, but one can show that. So if I just do this definition and for an arbitrary U0 and sigma 0, then it follows immediately that U of sigma 0 is actually U0.
They claim that there is no sigma 0 such that I can always go to any other sigma set. Is the third law.
You're asking what does the third law help? Yeah, so the third law talks about how whether we can reach certain states with a finite amount of resources. But of course, you could always go in the opposite direction. So if you have, for example, a 0 temperature state, hypothetically, I could look at the processes from there to somewhere.
Exactly. Because you said that there is no sigma 0 such that I can go to any other sigma set.
I mean, this could be, in principle, this is not excluded. Here, the framework just is also applicable if you don't have such a state. So the first law is phrased in such a way because you don't want to assume that there is a state from which everything else can be reached.
Okay.
So just to be on the careful side, so, which is usually, yeah. Yeah. Depends on whether you want to include the zero. Yeah, I mean, if you have an order relation, yes, this would correspond to that, right? It would be a maximum or minimal element, however you define the order. So, but we are not assuming this exists.
If I go to sigma or to sigma 2, though this is a complete order.
Aha. Yes. Okay. Yes. Right. Yes. That's right. Yes. Yeah. In that sense, we have a complete order. Yes. Okay. Now I see what you mean. Yes. Yes. We have a complete order implied by this first. Yes.
So there should be a minimal and maximum.
First, the question here.
Sigma 1 and sigma 2 was connected by multiple process, then they have same work cost, you mean?
Yes, that's what the first law requires.
So if I drive the system very fastly or very slowly, like isothermally or like adiabatically or something like that, very, as someone said, very fast or very slow,
Yes.
they have same work cost?
Yes, right. If it's not, for example, if you compress the gas very quickly or very slowly, if the gas is not in contact with the thermal reservoir, then at the end, the energy will be the same in the final state and the final volume is the same. And I mean, you can convince yourself this is actually the case because I mean, the important thing is this is a process only involving the system. So there's no energy exchange allowed. Usually in practice, you compress the gas very quickly and compare it to a slow one. There's a difference because for the slow compression, the gas has time to radiate heat. Okay, so it's really good that you ask all these questions.
Excuse me.
Yes.
Would it be right to interpret that a system S is not a system, that a subset S is not a system if it does not satisfy the first law?
Yes, and by the way, I mean, generally you can say, take all axioms together, and then you can ask yourself, what do you need to include in your thermodynamic world in order for the axioms to be consistent? And you could now say, if you find a system for which this is not true, we just exclude it from that set of axioms. So that's actually the nice thing about axiomatics. You can somehow, I mean, you could go the other way around and say anything in the world that satisfies the axiom can be now treated as a thermodynamic system. Now that's here. Yes.
You were saying that this old framework idea is to apply to kind of very exotic situations such as whole physics and so on.
Yes.
So, and all of the postulates before were very natural. So do you think this assumption of having a total order is something that we should take for granted also in those sort of situations? So it could be interesting.
Yes, so that's exactly, I think, the interesting part of developing such framework. We need now for black holes to verify whether such a thing holds. And that's a non-trivial task in general. So, but yes, so we could say that if it doesn't hold, then we may have to separate, let's say, the class of states of black holes into two parts and say we can only, we have to restrict to the states which are connected in a way. I mean, in this diagram, there could be a kind of disconnected subset of states. They only process among them, and you can never connect this subset of states with that. And then we would have to say, let's just separate the whole state space and say, this is now our thermodynamics theory, and this is a separate one, and we have to treat them separately. And we would not be allowed, for example, then to compare some derived notions like entropy from here to here. So this is exactly a good sanity check to see whether, for example, the notion when we define an entropy of the black hole is actually well defined. It is only when you can do that. Okay, so now comes the definition of heat. And after that, I will no longer go into details and just give you kind of an overview of what follows. Because once you see the principles, everything is then kind of following, in a way, the principle. So heat, Q. So for any process P, which is not necessarily restricted to a system S, the heat change or the heat delivered to a system S within that process is defined, and now I think this is now what you would usually call the second law, is defined as the I mean, I haven't introduced this notation really. This just means U of the final state of P minus U of the initial state of P minus the work delivered to the system. Okay, so that's now something one has to maybe digest a bit, but what does it tell us? It tells us take an arbitrary process which now not only acts on a system S itself, so think of here I have a system S and here I have a reservoir, and now I somehow do a process on the system and the reservoir together, so they could be connected. Now, in order to define how much heat did flow into the system, I take the change of the internal energy of the system, which is now a well-defined notion, we defined this just before, minus the work that is explicit. I mean, there's some explicit work. Maybe you should think of this as a piston, for example, or a cylinder with a piston again. That's always, I think so. You also put some explicit work into the system by pushing the piston. So work given by the work function. But there could also be some heat flowing into the system intuitively. And the heat is now exactly defined in that way. It's a difference of the energy you have in the system during the process minus the part you put in a controlled way, namely the work. So in other words, heat is really defined as the energy that flows into the system, which is not accountable by the part which you do in a controlled manner. And by controlled manner I mean that you actually put work in it by this work function. So the work function captures what you really put in a way that is controllable from the outside. For example, in this process, in the black hole, we have this thing that you lowered, and you know how much work goes in, but maybe there's also some heat going into the system, and that is just the difference. So you look at the final energy of the, for example, black hole minus the initial one, and then subtract how much work did you actually put in, and then the rest is heat that had to come from somewhere else. Yes.
If the system is connected to the hot bath, while the wall in between can move, which is not in control of the observer, so it still works. So the control is not a very good work.
This is now very good. So actually, the distinction between heat and work in general is actually dependent on us in some way. How does this enter? He chose at the beginning of the framework what are the macroscopic variables, and remember the axioms are very much bound on what are the states. If I, for example, have a moving wall and I don't include the position of the wall into the state description, then the framework looks the same, but the implementation of the framework is a bit different. I have different processes. For example, I cannot explicitly move that wall and so on. And in that case, so if I don't describe the position of the wall as a variable in my state space, then this will count as heat. But if I say, no, this is something I know, then I include it as a state variable. So it's part of my sigma, and then it's work. So in some way, we make a big decision at the beginning when we say these are the variables we are describing, because these are by definition the things we know and we control. So everything that goes into the system via these controlled quantities is work, and everything else is heat. But the distinction is not given by nature, it's given by what we choose to describe. Of course, in the case of black holes, you could say the choice is made by what Einstein chose to be part of general relativity, and everything that is not part of general relativity, the microscopic degrees of a black hole, they are kind of heat, and everything that is part of the general theory of relativity, like the mass of the black hole, its charge, this is part of the work. But this is somehow an artificial distinction, but it's important to notice that. That's one of the things that this framework should help you to make this clearer in your mind. What is the distinction between work and heat? It actually comes from a choice we made. And this is very important to understand. So these are exactly the type of questions one can hopefully better understand.
If you consider it as heat, it should also change the entropy when you define it.
Now I'll come to that. So now is the part, so now I gave you kind of a rather, this was rather detailed what I told you so far. Now I will just tell you how it proceeds. So the next thing one actually does is one defines temperature, and there is this now this theorem one can. Oh no, I forgot the most important thing. There is the second law. that's maybe kind of the most important part of the lecture. What is now the second law? Because that's usually very vague. When you look at the literature, what is the second law? It says something like, if I do some, or I mean, sometimes it says entropy can only increase. We haven't yet defined entropy, but it says, if we somehow look at machines and the reservoir, this and this happens. So it's in words somehow. Now to define the second law, I have to consider what I call a reservoir system. Now, what is a reservoir system? As I said, a reservoir system is just a thermodynamic system. But I will assume that it has some additional properties. So a reservoir is a system, actually, I assume it has only little properties. A reservoir system is a system where the function U, the internal energy, that's a requirement, that's what I mean by reservoir, is injective. What does this mean? That sounds a bit mathematical. So U is injective actually means that the only property the system has is its internal energy. So if I know its internal energy, I know its state. So it means that the reservoir is kind of the most simple system you can imagine. It has no handles on it. You cannot measure its volume or anything. It's just a system and you know its internal energy, you know all, I mean, it doesn't mean you know everything about the system, but you describe it in the most coarse-grained way. Of course, in reality, the reservoir could be very complicated, but the point is, in our choice, now relating to the question of what do we describe, we say a reservoir is something we only describe in such a coarse-grained way that we only see its internal energy. Then, and also the reservoir should have the property that when we do work, we cannot extract work from it. So it doesn't, so for any processes, we cannot get work out. So this just means a reservoir doesn't have something like a piston attached to it. So we cannot, essentially, we cannot couple it to something mechanical directly. Of course, you can draw heat out, but it's not part of the reservoir. That would be, so if we can, of course, couple a reservoir to another system and then use it as an engine, but the reservoir itself doesn't have a mechanism to draw energy out. And then there's a third property, which I call transitivity. See? Under, okay, this I will only write small, this is not so important. Under translations of U. So it means that if I take the reservoir and increase its internal energy, it has in terms of what processes are allowed. Now with the reservoir, it's still the same system. So in some way, and when I put energy into a reservoir, it still behaves the same afterwards. So this captures somehow that the reservoir is infinitely long. So this is just, you don't need to understand this in detail. This is just to make clear that there is a precise way we can talk about reservoirs in this framework. And the details will not be relevant for what I'm going to say.
So again, transitivity under?
Transitivity under translations of U. Now the second law said something about such a reservoir system. So what does the second law now tell us? The second law, or its postulate, says, so that's still, okay, right again, second law. So all processes which act on, so on a system S and the reservoir R. So R is the reservoir and S is an arbitrary system which are cyclic on S. So I think that's all I need. Yes. And we have that Ws of P is larger or equal than 0. So that's, you see now it's a very mathematical statement, the second law. There's no vague words and so on. Everything is well defined. So we know what processes are. It just says any process you can imagine, which you can carry out on such a combined system of a reservoir with a system S, but nothing else. So this P SR means you're constrained to this thing, has the property that you will not get work out. So by the way, I mean, W is always, the sign is chosen, I forgot to emphasize that, such that when it's positive, you put work into the system. So this really means you put work into, so whatever, however clever you are, the process will always have the property that you never draw work out of this thing. This is this intuitive thing that you may have heard. If you just have one reservoir and not a second one, you cannot get any usable work out of it. And that's a postulate. That's and by the way, in general relativity, this is actually proof. So you can prove that in a way that this holds using or under certain other assumptions within GR. And so in that's then how general relativity connects to thermodynamics. You prove these things and see, they actually satisfy the postulates. Therefore, we can apply this whole framework and draw conclusions about Hawking radiation and so on. And that's part of what follows in a few minutes, I guess. Okay, now I'll just make the last statement. From this, this was the wrong board. I'm sorry, Lydia, but it's okay. I'll continue here.
Okay.
I'll need 5 more minutes. Is this?
Yeah.
Okay. Now all the notions I talked about before are now actually notions I can derive from what we have. So let me just give the example of temperature and heat. I haven't talked temperature and entropy. I haven't talked about temperature up to this point. And of course, there's again a nice feature is we can now just see it as a derived notion. So in order to define temperature, so one actually looks at a concrete setup consisting of 2 reservoirs. This sounds a bit artificial, but that's what one does. And that's actually not something that is new to that framework. That's kind of Carnot's theorem, if you look at in conventional books. There's a theorem that you can now prove rigorously within that framework. So given all the postulates I told you, we can now prove something. And the proof is the following, or the statement is the following, that for all processes P on this setup with 2 reservoirs, R1, R2, and S, and it is, and for all reversible processes on the same set, R1, R2, S. So I take an arbitrary process and I take a reversible one. It is true that the following holds. If I look at the heat that comes out of reservoir 1 in the process P, and I take the division by the heat that goes into the reservoir 2, and I compare this, and to make sure I get all the signs right and so on, I compare this to the heat that comes out of reservoir 1 in the process P prime. Sorry, this should be a P prime. So I have an arbitrary process and I have a reversible process. And I look at the fraction. So this is kind of, what's the fraction of heat coming out here? So that's I have a minus sign divided by how much heat goes in here. That the fraction of this for an arbitrary process is always bounded by the corresponding fraction of a reversible process. So that's maybe what you have seen as Carnot theorem. This should be familiar. The point is now this can be proved from the postulates we have seen. Yes?
To define what a reversible process is?
Yes, it's a process which has a process that does the opposite state transformation and the opposite verb. I didn't write it down, unfortunately. Yes, I only said it in words. So, really, in a rigorous way, a theorem. It's not somehow a vague thing. And the theorem implies, because if P is also reversible, then there has to be an equality, obviously, because then you can just turn the roles around and say it should also hold in the opposite direction. So it actually tells you that for any 2 processes, this ratio is always the same if it's reversible. So whenever you have in this setup a reversible process, the ratio of heat taken out here and going in here is the same. That's kind of the consequence. And that's why you can now say, this is just a function which I call tau, which is only a function of the reservoirs. So it doesn't depend on the process. So whenever we have a reversible process acting in a way which is sorry, I forgot to say something. This should be cyclic on S. I usually just put this into the drawing. Whenever I put a cycle, it should be cyclic on that system. So any cyclic process has to have this property. And now the point is that I can now define temperature in a very similar way as I define heat. So the temperature of a reservoir, so one first defines it for reservoirs, and one can then generalize this to arbitrary systems. So the temperature of a reservoir is actually defined by the ratio or by this tau of R to a reference reservoir with some reference temperature. So you see probably the similarity to how I define internal energy. So one just says, I take one reservoir, call it R0, and say this has temperature T0. It's just by definition. So the whole definition is up to a rescaling. And then I say for an arbitrary other reservoir, the temperature is given by this function tau, which by Carnot's theorem only depends on R and R0 times tau 0. And one can now define that, or one can now prove in the same way as for internal energy that this is well defined. So if I take different reservoirs and so on, this all satisfies this, but that's not something I can do. Now the very last point is, now we have, okay, I think the important message here is we can now define temperature really based on the postulates. There is no additional intuition or vague notion that has to come in. Intuition maybe should come in, but not a vague notion. It's just defined entirely in a rigorous manner based, like in group theory, when we define something. And we can do the same with entropy. Yes. And here I will again only give an overview. So if I have a system, maybe I immediately write down the definition of entropy. So the entropy of S of a state of a system is defined as some reference.
Right.
Yes.
Naive question, but is this standing for entropy or is it from the system?
Oh, yeah, this is unfortunate that in the literature yeah, so yeah, let's put here a kind of bold face S. So this is now entropy. This has nothing to do with the system S. And okay, now I have some S0, so that there's some reference. Okay, so this is again like we just define some system to have some reference state to have some entropy 0. And now I add to that the delta, the amount of heat that flows into a system. So let's now take, yeah, this is really unfortunate about the notation. So the system I make blue. So this is a state on a system S. And now I look how much heat flows into the system divided by a temperature. So what I mean by that is that I have, again, a system here, and I have a reservoir that has a certain temperature, and I have a process acting between the two. And now I just, so the reservoir has a temperature T that was defined. Reservoirs have temperatures, and I can now ask myself, so this is for a process P, and the process P is a reversible process P with initial state sigma 0, final state being equal to sigma. So that's somehow, again, well defined. I mean, you can just say entropy is now basically defined in terms of heat and temperature. This is again quite close. I mean, this is basically the usual definition, but now I think the order was different from how you usually learn it. So the order of the whole way concepts were introduced is that we never had to introduce a thermodynamic notion from scratch, so to speak. Now, I will not have time to prove any theorems, but there is an important theorem I can now also prove, which is for a closed system. If I look at the entropy of a process P, and I look how does the entropy behave, then the entropy of the final state is always larger than the initial state on a system S if P is only acting on S. Okay, now I think I'm actually done. I will not write anything further. I'll just give some explanations again. So, okay, for the definition of the entropy here, this was a process which acts, sorry, here I should have maybe written PRS. So let me still write that. So, so the entropy was defined by looking at processes and see how much heat do I supplement to a system at a certain temperature, and this defines me the entropy. And then again, in a similar way as for the internal evolution of temperature, one can prove that this is well defined. It doesn't actually depend on the process. So whatever process you take and whatever temperature T you take here, you will always get the same entropy for the same state. So entropy is a well-defined notion, but entropy is now defined completely independent of information theory. It's really defined in the very thermodynamic sense as the amount of heat going into a system. And now if I, however, restrict myself to processes which only act on S, so this P was acting on the system in a reservoir and there was some temperature. If I now isolate the system and look at a process only on S, for example, I take a wall out of a gas or I do something on an isolated black hole, then this is now a theorem. We can prove that the entropy only increases, or cannot never decrease. So this usual law that we know of, entropy can only decrease, follows now as a theorem, basically you can say from the second law in a very rigorous way. Okay, let me just briefly summarize and then I'll take questions. So that's now the end. I just want to maybe briefly tell you what we did, just if you now look back. So the idea was that we can start our thermodynamics from things that are very operational. So we have systems, we can act on them, we can modify some of their properties. So the properties are the states in the state space sigma S. And then we have certain physical quantities are actually mostly one, namely the work we can assign to any process. And the processes and this physical quantity have to satisfy certain postulates. The two most important ones are, of course, the first and second law, namely that if I change if I apply this process, then the work should be independent of the path or of how I do the process, only depend on initial and final state. And the second law, which is here, which says something about how much work I get if a system is connected to a reservoir. And then from these notions, we could move on and say, we now define stuff like heat, temperature, and entropy. So they are all derived notions. They didn't have to be introduced in the first place. And they were useful notions because we have, for example, this statement about entropy. And this statement immediately tells us which processes are possible. I mean, if you now ask questions about the thermodynamic world, that was the goal. We want to answer questions. Can, for example, a black hole shrink by itself without being in contact with something else? Then we calculate the entropy of the black hole later and earlier and see, if it shrunk, it would have a smaller entropy. So it cannot shrink because the entropy always has to increase. Okay, we always knew that, but the point is now we can, this is now a rigorous argument because general relativity allows us to verify that the postulates hold, of course, under certain assumptions within GR. And then we can apply the framework, which tells us these, gives us these answers in thermodynamic terms, and then we can translate them back into statements that are of interest to us, like this question about black holes. And the more interesting question is, of course, do black holes radiate? And that's what Ladina will tell us later today. So I think this was it, basically. I hope I could just give you, I mean, the idea was more to give you a flavor of how we think, rather than present you the whole framework, because to go into all the proofs would require substantially more time. If you're interested, as I said, they are either on YouTube in German or in Philipp Kammerlander's thesis. But I think the take-home message is thermodynamics can be put on a very rigorous and logically consistent footing. It's not about vague notions which have to be produced in the first place. And therefore, it's also, and the results we get, for example, in black hole thermodynamics are actually very solid results at the end. And yeah, I hope. Now, if there's time, I'm happy to take questions.
There's one question on YouTube, which is, how does this relate to the microscopic picture?
Yes, so as you probably noticed, I didn't talk about the microscopic picture at all. And that's, I would say, the big advantage of the framework, because, for example, in the case of black holes, we simply don't have a microscopic picture. So I think the answer is it doesn't require a microscopic picture whatsoever. And that's the big feature of this approach. That's why it's so interesting, because we need it in cases where we don't have it. Now, if you have a microscopic picture, you can relate it. There are proofs you can make, for example, to show that this entropy, which is kind of a remarkable proof in a way, this entropy is clearly defined independently of information-theoretic concepts. It talks about heat. But now you can also prove, once you have a microscopic picture, that this entropy is actually equivalent to the information-theoretic or statistical mechanical entropy. This proof can now also be put on rigorous footings. That's, by the way, also in the lectures I mentioned before, if you're interested. And so in that sense, if you have a picture that is microscopic, you can relate these notions to the corresponding statistical mechanical notions that are well known. I think there was another question from here.
Yeah, it's about the computer.
Yes.
So, like, let's say we are making a measurement.
Yes.
And then maybe you are using some addition on the box. So I don't know how you control the temperature, because sometimes when we are making the measurement, the gas is still moving. At some point, the cloud has full. And then you need to cool it down again.
Yes, okay, so the point is you're essentially describing a situation where during the measurement process things change in a certain way. Yes. Yes. So yeah, that's a bit related to the question that was asked earlier. Do systems have to be in thermal equilibrium? And I said they don't, as long as you can extract the quantity. So here the question would be, I mean, I cannot give a specific answer to your setup because I don't know it in detail, but the general answer is, in order to apply this framework, you need some way to have a reproducible number you can assign to the system. So for example, you could say you can repeat this measurement many times, and maybe you have always the same, let's say at the beginning, before things explode, you have the same behavior, and you take this, you extract some, you take some quantity that characterizes this behavior. And this could even be a statistical quantity, but if you repeat it many times, this gives you, for example, an expectation value. And then you could say that the state space is actually the expectation value of such a process. So the point is, if you look at the framework, the only thing we require is that the state space is a set of numbers that are in principle somehow can be determined in order to make this physically relevant. And if there are fluctuations, you have somehow to deal with this by taking averages or repeating the process and so on. But unfortunately, I cannot now comment on the very specific case. Maybe you can later tell me more details about it. Yes.
Here you have written for the second law for this SP is larger than the SP of the initial state. And you have written that T is in capital TS. It means that this increase of entropy comes from the internal dynamics of the system. Yes.
Yes. Right.
So this gives us some information. If you, I mean, can we use it for a black hole? Because as you said, we are not aware of what is happening inside the black hole.
Yes.
If this inequality holds there, so because for example, if we have when in a free expansion of a gas, we see that it always expands. It never shrinks. Okay, so it means that the dynamic, whoever who created this world or whatever, if it's God or whatever, it's been created in a way that it always expands. So I'm asking, does this inequality give us some information about the internal dynamics of the black hole?
No, it doesn't, but it still gives us an important information because, for example, take the system to be a combination, let's say, of two black holes. So as I said before, we don't have an internal theory. So of course it gives us indirect information. So whatever the macroscopic theory is, it has to be compatible with this. But concretely, what it tells us is the following. Let's suppose you have two black holes and the two black holes somehow merge. Now, okay, later in time you have one big black hole. Now you could ask the question, I mean, we will see in the next lectures that you can calculate the entropy of a black hole. Now you can take the two black holes as one system. And this system is isolated. So let's suppose there are just these two black holes in the universe and they somehow collide. And in that sense, the process of them colliding is now a process on S, where S is the combination of the two black holes. And now the fact that the entropy increases tells you something about the size of this. So more specifically, you can, for example, you will see that the entropy corresponds actually to the area of the black hole. Now this thing tells you immediately that the area of the new black hole that is created has to be at least as large as the sum of the areas of the two initial black holes. That's something, by the way, that can be also derived from basic notions in GR. So it's kind of a consistency check. But you could also, let's say, I mean, there are two ways to arrive at this result. You can first get to the entropy formula for black holes and then use that thing and say, oh, from this we learn that the area of black holes, if they combine, has to be larger. You can also do the whole calculation within GR without ever going to thermodynamics, because it's just about areas and the two are consistent. I mean, but they're very different in a way. And of course, you can now also maybe make statements that you couldn't derive within GR potentially or haven't been found so far. So it tells us something about general relativity, but now you say if we now find at some point an internal theory or a microscopic theory, then as I said before, for those cases where we have microscopic theories, we can relate the thermodynamic entropy as defined here with heat to the statistical entropy. So we know that the statistical description of a black hole has to be compatible with this. So for example, the number of degrees of freedom of a black hole cannot be larger than the area of the black hole. That's one thing we can learn about the microscopic theory without having it, so to speak. So in a way, it gives us hints about it.
Okay, so I will thank Renato here. And if you have questions, you can ask him here or downstairs at the coffee. We restart at 12:30. Thank you, Renato.